Let's look at this problem. A square loop whose sides are 6 centimeters long is made with copper wire of radius 1 millimeter. If a magnetic field perpendicular to the loop is changing at a rate of 5 millitesla per second, what is the current in the loop? Okay, so let's get a diagram going first. It's a square loop and side 6 centimeters L. Okay. If a magnetic field perpendicular to the near the magnetic field, and they tell us dB by dt is equal to 5 millitesla per second. What is the current in the loop? All right, let's since we'll need to find the current in the loop, let's find the resistance of the loop. The resistance of the loop is the resistivity plus the length divided by the area of cross section. And let me look up the resistivity of copper. The resistivity for copper. Okay. Okay, resistivity for copper is 1.68 into 10 minus 8 ohm meter. The length is 4 times 6 centimeters, and each centimeter is 10 minus 2 meters. Okay. And the area of cross section is pi r square. R is 1 millimeter, so 10 minus 3 meters square. Okay, and R, the radius of the copper wire, is 1 millimeter. Okay, so let's figure this out. Again, let's take care of powers of 10. This is 10 minus 8, 10 minus 10, and there's 10 minus 6 here. So you are left with 10 minus 4 at the top. And the other factors are 1.68, and of course it'll work out in ohms, into 24 divided by pi. Okay, and this is equal to 12 point, so 1.28, so 1.28 into 10 to the minus 3 ohms, 1.28 milliohms. That's the resistance of the copper wire. Okay, we still have to find the EMF developed in the loop. Okay, let's add a page. Okay, the flux is B times the area, B dot area, and since B is perpendicular to the area, it's B is perpendicular. B and A are okay. B and A are parallel to each other, so this is B times A, and that's equal to B times L square. So, all right, so that's flux. And so the EMF induced is d phi by dt. We are just interested in the magnitude of the EMF, so we'll take the absolute value of that. and the area is not decreasing, so dB by dt times L square, the area is not changing. So the induced EMF. Okay, and what is it that we are trying to find? What is the current in the loop? So the current in the loop is the EMF in the loop divided by the resistance. So it's 1 over R times L square dB by dt. Okay, so R is 1.28 into 10 minus 3 ohms. L square is 36 centimeters square, and to convert that to meters, that's 36 times 10 minus 4 meters square, and dB by dt is, they give us that as 5 millitesla, 5 into 10 to the minus 3 Tesla per second. Alright, so all those units should, they're all in SI units, they should combine to give you amperes. Okay, let's take care of powers of 10. This 10 minus 3 cancels with that, there's 10 minus 4, so what you have is 36 times 5 divided by 1.28 into 10 minus 4 amperes, and that's equal to 140 14.1 into 10 minus 3 amps, 14.1 milliamps. Okay, so that takes care of that problem. Okay, let's see, is there anything else? Alright, that was it.